Okay, as we complete the halocarbons here, we've talked about naming and properties. We're going to talk about uses here now to finish this off. So alkyl halides, which remember is the name for carbon chains with the halogens on them, are often used as starting materials in the chemical industry, because halogen atoms attached to carbon are more reactive than hydrogen atoms. So because they're more reactive, they get these chemical processes going in industry in order to mass produce other chemicals and different commercial things. They're used as starting materials. They're also used as solvents and cleaning agents. So if you remember, solvents are things that will dissolve other things. So if you have sticky, mucky, grimy stuff, solvents, they will dissolve a lot of things and break them down. PTFE, that's polytetrafluoroethene. Polytetrafluoroethene is a plastic. PTFE is a plastic made from gaseous tetrafluoroethylene and is made up of hundreds of units and provides the non-stick surface for bakeware. So if there's a lot of bakeware that says, non-stick surface, and that's from a plastic made from halocarbons, non-stick surface. Another plastic is polyvinyl chloride. You've definitely heard of that one. PVC, like PVC pipes for plumbing and stuff like that. That can be manufactured soft or hard as thin sheets or molded into objects. And like I say, the PVC pipes are very common in plumbing. They don't use the metal pipes anymore, so they don't corrode. These are easy to make, and they last a long time and very resistant to corrosion and stuff. Okay, so there are some uses for halocarbons: reactivity, starting materials, solvents, non-stick bakeware, and PVC piping. All right, let's just get some more practice here to round out our study on halocarbons here. I've got 3 structures here. If you remember from last lesson, let's see how well you remember these ones here. So go ahead and take a few minutes on your own and name each one of these 3. And I'll give you a few minutes to do that, and then we'll check on your answers. I'll give you the first answer here behind this cleverly placed blackout here. I'll give you that in a minute just so you can check to see if you're on the right track. Okay, go ahead. All right, so let's go over the answers here. I've had a chance to do this. Number 1, or letter A there, okay. We have, we're going to isolate here our bromine, we have fluorine, and we have another halogen over here, another bromine. So we want bromine has to be listed first because of alphabetical, and we want it to have the lowest number possible. So we'll start from 1 at this end. 1, 2, 3, 4. Oh, it's frozen? Oh, I thought I hit that button. Okay, thank you. 5, 6, 7. So we'll name them like this, 1 through 7 over here. So we're going to have 2, 4, because we've got 2 bromines, so we have to do list both numbers. Between a letter and a number is a dash. Between numbers is a comma. We do have to also say di, because it's bromine, it's bromo. Okay. Between a letter and a number here should be a comma, 7, dash, fluoros, because we've got fluorine here on the 7th one. And yeah, again, you have to keep the numbering consistent. You can't start over from 1 here. You can't say, oh, this is now 1 on this end. This has to be 7, and it's fluoroheptane for single bonds, or septane, okay? Heptane or septane, I think they're both equally as valid. You'll see both of those. All right, so that's for A. For B, down here, I don't know what you look for first. If obviously you want to look for your halogens. 1, 2, 3, 4, 5, 6. There's 6 carbons, so that's going to be hex. It's all single bonds, so it's going to be hexane. If you want to jot that down first, I don't know. But we have iodine and fluorine, so A, B, C, D, E, F, G, H, I. So F comes first, so we're going to start counting from here. This is going to be 1. That's going to be 2, okay? Now, this is a bit strange here, but you do have to do 2, 2. If you just do 2 dash, you got to do 2, 2. Okay. Again, we're going to try and keep the naming as consistent as possible. So 2, 2, because the fluorines are both on the 2nd carbon in the chain. 2, 2 dash difluoro, because there's another one we have to now account for that. Dash 1, 2, 3, 4 iodo, hexane. Iodo for iodine, hexane. Okay. Yeah, question? You use a comma between numbers, dashes between letters and numbers. So if it's a letter and a number, then it's a dash. If it's two numbers in a row, it's comma. So there's a comma between the two numbers. There's dashes between the letters and numbers everywhere else. Okay? Yep. Oh, an A here? Oh. Yeah, that should be a dash. Thank you. That should be a dash. Letter and number is a dash. Okay, C. So let's talk about C then. Now this is benzene, so you're going to have to end with benzene. Which one comes first in the alphabet? Bromine. So we got to list bromine first. It has to have the smallest number, so we can start anywhere, remember, on a benzene chain, right? So we're going to start with 1 here. So this is going to be 1 bromo, 3 chloro. Why do we go with 3 chloro? Well, C comes before F, so you want to keep the numbers low for the lower, for the letters in the alphabet. So we're going to go 1, 2, 3 this way, 4, 5, 6. So 1 bromo, 3 chloro, and then 5 fluoro, and then the base kind of molecule they're attached to is benzene. Okay, any other questions about that? Okay, draw these structures. Draw these structures. So you had to name, now draw. Go ahead and take a few moments to do that. Okay, so there's A. If you drew the H's extending out, that's fine too. 2 chlorobutane, this one should be pretty straightforward. 2 chloro, so that means on the second carbon, there needs to be a chlorine. If you drew it like this, where you had C, 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 and then you drew it over here for whatever reason, that's fine too. That's still 2. It's all the same thing. It's just the same molecule except it's flipped around. Like if you just take your hand, put it in front of you, then you flip it around. So both those are okay. And if it goes up, that's fine too. If you draw it on the up, whatever, it doesn't matter. If chlorine extends up instead of down, that's fine too. Okay. 1,3-difluorohexane. Okay, so again, when you're drawing, I'm not sure where you want to start with these. If you want to start with I would probably start drawing with the hexane, right? 1, 2, 3, 4, 5, 6. Probably a good idea. The 1 and the 3 talk about where the 2 fluoros are. So there's 2 fluoros on 1, and you can draw just an extension, C with the F on number 1, and then on number 3, they can both go up or both go down, or 1 up, 1 down. Typically, probably would be better to draw 1 up, 1 down, because remember they're really huge. They're really huge atoms compared to hydrogen, so they'd want to spread out as much as possible. All right. Yeah, 3. Sorry, should be on. Yeah, the third one's over here. Yeah. 1,3-difluoro. 1, 2, and 3. So they can go up or down. Other ones would be best. 1, 2, 3, 4, 5, 6. All right. C. 1,1,1 trichloroethane. Okay, so 1,1,1 means that we have the 3 chloros, all on the same carbon, and that would be the first carbon. So it has chlorines, 3 chlorines there, and it's an ethane molecule, so singly bonded meth F to 2 carbons. All right, 1 bromo 4-chlorobenzene. So we have a benzene. Good idea to draw the benzene there. And again, 1 can be anywhere. It doesn't really matter where you start. Doesn't matter at all. But what does matter is where the chloro is. It's on the 4th. So count either direction. Doesn't matter. 1, 2, 3, 4. It's really the opposite side, so it doesn't really matter which way you count. And that's a chloro. So a Cl there. So 1 bromo 4 chloro, and again, doesn't matter which way you count. This is 1 carbon, 2, 3. This is going to be 4 if you count this way. 2, 3. This is also 4. This one doesn't really matter. Okay, is that what you guys had? Any questions there? I'm making a real mess of this now, but yeah. Is it possible to represent number 3 like it is? Yeah, sure. Yeah. You could draw it like this if you want, like with the chloros all here. Is that what you mean? Yes, you can write like that too. Yeah. I'm sorry. Like you can write it like this too. So there's going to be Cl. Well, this one with the groups, you should actually extend those out. Yeah. So Cl. But you could do this CH3 if you want. Yeah, sure. Yep. That's fine. Okay, good. All right. Okay, let's move on to alcohols. Let's study the alcohol group. What makes that, these types of chemicals, what makes them alcohols? We discussed this in one of the first lessons when we started the organic chemistry part. So an oxygen-hydrogen group, so this should be, this should be on your the first page of the notes that I gave you. These notes got out of order a bit, so as long as you can find out where we're at. An oxygen-hydrogen group covalently bonded to a carbon atom is called a hydroxyl group. Talked about this last lesson. Hydroxyl group, and that's an OH like this, right? Just straight OH. It's not OH minus, right? You don't put a minus on there. It's just a fully. There's no charge on the group there. An organic compound in which a hydroxyl group replaces a hydrogen atom of a hydrocarbon is called an alcohol. So it's a type of molecules, and yes, in the alcoholic drinks, yes, you'd have alcohol molecules. All right, the general formula for an alcohol is ROH. Also, as we discussed yesterday with that little chart, also sometimes there's just a little bond between there too. And R is a carbon ring or chain. Okay. All right, so how do you name them, okay? Or how do they happen? Well, here's the hydroxyl group that is kicking out this hydrogen and being replaced in there, okay? So the hydroxyl group attaches there. So methane, CH4, becomes methanol, all right? All. Methanol. This is what methanol looks like. Meth because of 1 carbon, and the all at the end because of the alcohol. So in naming, that's basically what you do is you take off the E on the end of a simple alkane chain. You take off the E and you put all at the end. That's pretty much it. So methanol, ethanol, propanol, butanol, and all that sort of stuff. If it's a cyclo, remember this is not benzene right here. It doesn't have the inner circle there. This is cyclohexanol. Cyclohexane with an all hydroxyl group there. In alcohols of 3 or more carbon atoms, the hydroxyl group can be at 2 or more positions, so a number is added. All right, that makes sense. So a number is added, so we've been doing so far, especially if there's more than one option. So methanol, ethanol, there's no options for where these can attach, right? Methanol, 1 carbon, so it just attaches there. Ethanol, 2 carbons. It could attach to the first one, or the second one is still the same as the first one, right? It's just the molecule flipped around. So after ethanol, okay, when there's 3 or more carbons here, then we have to start naming the position, because the OH could be on the first, or it could be on the second, as over here. And then those are the only 2 options you have. Because the third, if it attaches on the third in this naming order, that's the same as the second, right? It's just the molecule, again, turned right around. And if you think, well, what about the fourth one? Well, that's the same as the first one. It's just looking at it from the other side. So you have two options for naming only here: 1 butanol and 2 butanol. Okay. Yeah, it's not even really an isomer. It's the exact same molecule. Yeah, it's the exact same thing. It's like literally looking at your hand, putting your hand in front of you, and then turning your hand around. It's the same hand. It just looks different. So if I was to draw my hand with my palm facing you, I would draw it a certain way. If I turned it around and drew it on the paper, it would look different, but it's the same hand, you know what I mean? Just the perspective. Yeah. It's not really an isomer, it's actually the exact same thing. Okay, you guys got that? So there is no 3-butanol, right? You wouldn't name it that way. Keep the numbers small, only 1 and 2. All right, if a compound has more than one hydroxyl group, then prefixes are used, okay? And again, as we move through this, organic chemistry has been around a long time. It's universal, but on the same hand, it's been developed independently across the country and so across the world. So there are some different conventions, right? Like for naming and stuff like that. You will see as we come up here pretty quick, you're going to see slightly different ways of naming. We're going to try and just focus on the most common ways of naming, but you'll see common names like this, which that's not a different way of naming. That's just a common name. But you will start to see that there are going to be 2 options for correct names, okay? I don't want to confuse you with those, but just in reality, this is a huge, huge subject. I mean, I've got my organic chemistry textbooks from university in the back shelf over there. They're the biggest ones back there, okay? It's massive. It's a massive, massive subject. And when I got into organic chemistry, the first time I started learning this stuff was in university. It wasn't in the core curriculum when I was in high school. And so when I got into university learning this stuff, it was like a punch in the nose. Like seriously, I was like, what the? It's such a huge area. So this is good that you're learning this now. If you take chemistry in university at all, they're going to be throwing this at you 100 miles an hour. So to know the basics is very important. But on the same hand, the more you learn, and this is what I found in university, the more you learn about a subject, the more you realize you don't know. Because these subjects are super huge. And when you take introductory courses, a lot of times it's just the surface stuff. It's just to get you by, just so you can kind of like know a little bit about what you're doing so that you can learn more about it. So I'm going to try and be as consistent as possible here, but you will find that there are multiple ways of naming things, but we'll try and keep it straight for you. So if there's more than one alcohol group, everything's the same so far. We use the numbers here. So this is a bit messy here, but so this would be 1, 2, 3, okay? Propana. Now, here's the other thing. The tri, remember that was on at the beginning of the alkane groups there? At the beginnings, the 1, 2, 3 tri, remember it was at the beginning of the halocarbons and that? It's not at the beginning here, okay? It's propana triol. Propana triol. So for these alcohols, the tri is after the parent group. Don't ask me why. Okay. Now the common names, you'll see common names, and these chemical names can get super huge and complicated, so that's why we don't use them very often. It's just referred to as glycerol, but there is obviously a proper chemical name for it. So let's get some. We'll talk about properties and that, and then we'll get some more practice naming. The hydroxyl groups of alcohol molecules are moderately polar. Okay, so they have a partial charge on either end, positive, negative. And they're able to hydrogen bond with hydroxyl groups of other alcohol molecules, giving them a much higher boiling point than hydrocarbons of similar shape and size. So compared to hydrocarbons of similar shape and size, they have a higher boiling point because of the interactions in between the molecules. Also, because of their polarity and hydrogen bonding, ethanol is completely miscible in water. Okay, so it completely mixes really well. It doesn't form like an oily drops or whatever like you would see with some things that try to mix with water. It's completely miscible with water. Because of their polarity, alcohols are also good solvents, just like we found with the last group we studied, halocarbons. They're good solvents as well. So the organic solvents are very effective, but very, they can be kind of dangerous, toxic. You have to be careful. But obviously, if you're cleaning a cut or something, right? If you got a cut or you want to disinfect something, that sort of thing, alcohol swab, right? Rubbing alcohol, that sort of thing. They're very good to dissolve other organic substances. Mm-hmm. Yeah, miscible, it's completely mixable. I think someone else really asked for the definition before. I don't know. I have. Just let me. Like I said, so miscible is capable of being mixed in all proportions. So it's just mixable, right? Yeah, miscible. So methanol is a common industrial solvent found in some paint strippers. 2-butanol is found in some stains and varnishes. Okay, so industrial solvents, very strong solvents. Paint strippers, you can't just wash paint off with soap and water. You need a strong solvent. And it's use. Uses, okay, obviously alcoholic beverages, medicinal products, as effective as an antiseptic as we mentioned here. Obviously, an antiseptic, as we talked about, it's also a gasoline additive. Okay, so ethanol in gasoline, you'll see if you look on the gasoline pumps, be a certain percentage of ethanol that's added for into the gasoline. Denatured alcohol is found on the shelves of drugstores. It is ethanol with small amounts of noxious materials. So, yeah, obviously, alcohol as a beverage, messes with your body chemistry, and that's why you get drunk drinking alcoholic beverages. Okay, I would advise that. But the alcohol that can be purchased in the drugstores, okay, for the antiseptic or for whatever reason, for cleaning and that sort of stuff, medical purposes, denatured alcohol, it's ethanol with small amounts of noxious materials such as aviation gasoline, other organic solvents to make it unfit to drink, so people don't buy it and drink it. You don't want to drink any alcohol you find in the drugstore. Not good. Cyclohexanol is a poisonous compound used as a solvent. Cyclohexanol for certain plastics and in the manufacturing of insecticides. Glycerol is often found in as an antifreeze, used as an antifreeze. And airplane de-icing fluid. There's lots of uses of the alcohol organic chemistry group there. All right, so naming alcohols here. We were to name the following alcohols. Why don't you go ahead and give these a try? I'll walk you through the first one here. So this is, there's 1, 2, 3, 4, 5 carbons there. It's in a ring, right? So there's only one alcohol group on there. What do you think you'd call this one? Okay, well, so 5 carbons would be penta, not hexa. So cyclopent, yeah, cyclopent. Okay. Now, would you need a number here? No. Could be anywhere. The numbers a lot of times are just for in relation to where the others are in the group. So you would. There was more than. What's up? Sorry? Yeah, you need numbers if there's more than one. Exactly. So this is just going to be straight cyclopentanol. Why do you use cyclo because it's a ring in a circle. It's not a straight chain. So this would be a straight chain over here, straight chains. But this, well, because benzene is its own name, like it's its own. So remember the cyclohexane is all single bonds. The benzene is still 6 carbons, but it's got that special, those resonance structures, the special bonding. Yeah, benzene's different than cyclohexane. Okay, go ahead and name these other ones. Take a moment to do that. Okay, so here are your answers for naming the structures in those these alcohols here. So now draw the structures here. Here's the first one done for you, 2-hexanol. So again, if you want to focus on the hex, right, you know that there's 6 carbons, so you can draw those first. The all here, and there's only one, because there's one number, there's no di or tri or anything here. So this 2 would be on the second one, whether you count it from the left or the right. I mean, usually we read from left to right, so you usually draw it, you count from left to right if you have a choice, but it would be okay if the hydroxyl was over here as well. Yeah, and I won't make you draw all the hydrogens here either, guys. So, but anyways, go ahead and take a shot at these other 3. Sorry, you're gonna have to talk a lot louder. I can't hear you. Yeah, listen. Yeah, right now we're drawing all the carbons. We're writing all the carbons. Okay. You will see this as well. Just like that as well. That is totally fine as well. Yes. Not sure. Any other questions about these here? Just get this on there. Okay. So just a reminder, this is chapter 22 in your Glencoe text. Chapter 22 is where it talks about your organic compounds and stuff like that. You'll see the charts, some of the diagrams that I'm using in the notes here are the same. And yeah, so page 784 is where that starts on. I'm going to get you to read through chapter 22. You can take the last 5-6 minutes of class here to please begin reading. Talks about everything we've talked about here, kind of fills in some blanks, gives you some examples, and there's also some questions that you can do as well. So at the end of each section, there's review questions. I would encourage you to do all of those. And some of them are just structures, some of them are just asking you some questions about understanding what you're learning so far. But yeah, just flip through the textbook and read through chapter 22. Looks like we've covered really up to, so far, where are we? Up to about 796 so far. So go ahead and read chapter 22.